Hello and welcome to Reading Potential Energy Diagrams. The potential energy diagram shows the amount of energy at different points during a reaction. There are several places on this reaction diagram that you need to be able to identify and do a little bit of interpretation of. Our potential energy of our reactants is indicated by A on the graph. This is the amount of energy stored in the initial chemical bonds that the reactants have. You'll notice that this starting amount of energy is not zero. We don't start out with zero energy. There's always stored energy in the form of potential energy stored in the bonds of the reactants. Where we end up is indicated on this graph as B at the very end of things with the potential energy of our products. This is a very similar concept, just on the other end of things. So after we go through the reaction, we then end up with an amount of energy that is stored in the bonds of the products. In the middle, we have this high energy thing called an activated complex. Sometimes that's also called a transition state. And what this is it's a high energy intermediate where we have things kind of have been rearranged a little bit, some bonds have been broken, but our products have not formed yet. So our activated complex can also be called the transition state. Or the high energy intermediate. And the potential energy activated complex is a very high energy state. This does not hang around long. It's literally a hot second. And then the atoms that are in that transition state rearrange and they form their new bonds. The idea of activation energy is really, really important. So we have to be able to get over this energy hump being depicted by C. We start with the amount of energy that we have as A. D, this amount of energy that we must put in to get there, is what's known as our activation energy. So this is the amount of energy that we need to get this reaction started. When you think about something like lighting a Bunsen burner, this is that lighting the match energy. Another really important concept is represented by E here, and this is also what we call the delta H, or the heat of reaction. It's called delta H because it's a change in energy. The heat of reaction is the difference between the PE of the reactant and the potential energy of the product. This is a net energy change, and this can be a gain or a loss. Now, if we look at the diagram up here, this is a diagram for an exothermic reaction. And the way that we can tell is we have a certain amount of energy that we start with, and we end at a lower amount of energy. So that means the rest of that energy was given away. So when we have an exothermic reaction, because we're ending lower, whenever we figure out our delta H is the energy of the products minus the energy of the reactants. Therefore, if we end higher, we have a negative delta H, and heat is being released to the surroundings. Whereas in an endothermic reaction, since we're ending higher, we're going to end at a positive, or we're going to end at a larger number, so it's a bigger number minus a smaller number, positive delta H, heat is being absorbed. So again, as we mentioned, that above diagram is for an exothermic reaction because heat is being given off or released. So that would be found to have a negative delta H value. In all reactions, there are two major steps. We mentioned this talking about the combustion of methane. We always have an initial bond breaking step. And that step is going to be endothermic, because in order to break a bond, we must put energy in. And then we follow this with a bond forming step, which is exothermic. Now, the reaction overall could be exo or endo, depending on how much energy is involved. So if in an endothermic reaction, it requires a lot of energy to break the bonds, and we don't end up getting that much back when new products form. In an exothermic reaction, we have a second step where there's a great release of energy that makes up for that energy input that we had to put in the first step. So if we want to look at a potential energy diagram for an endothermic reaction, again, remember, energy is being absorbed overall. So what's going to happen here, what's going to happen here is we're going to start down here. We're going to put a lot of energy in, and then we don't end up getting as much back. So that second step did not give us that much energy back. We should still be able to look at our potential energy of our reactants, our potential energy of our products, the energy of the activated complex, the amount of energy being put in, which is going to be our activation energy. And finally, we should also be able to look at the heat of reaction. I'll do that in blue to make it stand out. That's the difference between here and here, and we'll indicate that with E. So what makes this diagram different from the exothermic reaction is that the potential energy of our reactant is higher than the potential energy of the product. Therefore, when you subtract B minus A, you're going to get a positive number. So remember, whether the overall reaction is going to be exo or endothermic is going to depend on net changes in energy. In every single reaction, the first step is always endo. We always have to break initial bonds. The second step is always going to be exothermic. It just depends which one of those is larger, which one, whether the overall reaction will be considered exo or endothermic. So we have to be able to read a potential energy diagram with values given on it. So our heat of reactant is where we start, and that's given as 40. Our heat of our product, or potential energy of our product, is given as 20. And I do use those terms a little bit interchangeably. They're used differently in different places. It's a little frustrating because heat and potential energy are different things, but in this terminology, they're kind of treated similarly. Our potential energy of our activated complex is 50. Most of those are pretty straightforward to people. Delta H and activation energy are the ones that are most commonly confused by students. So our delta H, remember, is going to be where we ended up, okay? So where we ended up here at 20 minus where we started. So this is our delta H for this reaction is going to be our products minus our reactants. So since we ended lower than we started, we're going to get a negative number here. So our delta H for this reaction is negative 20 kilojoules. This is an exothermic reaction. I can see that it's ending lower and I have a negative delta H. Now my activation energy is the amount of energy that I needed to put in to get this thing going. So I started at 40, I needed to get up to 50. My activation energy is 10. So your activation energy is not equal to your activated complex because you already have some energy when you started. Now we have to look at something called the effect of a catalyst. So let's talk first about how a catalyst operates, and then we'll go back and look at that. So catalysts are substances that lower the activation energy of a reaction. These substances lower the activation energy of a reaction by providing an alternate reaction pathway. Now, catalysts are a very, very, very broad category. They include enzymes, they include a lot of non-biological catalysts. So there are a lot of ways that catalysts are able to operate. What a catalyst is going to do for us is reduce the activation energy of the reaction and nothing else. What's kind of neat about a catalyst is they don't actually get used up in a reaction at all. They're returned to their normal state at the end. So they're unchanged by the reaction in which they're involved. And they give us sort of what I like to call an energy shortcut. So to think about what a shortcut means, if I was going to take you to Walmart and we took a bus to Walmart, if I took the route to Walmart that's indicated here where I'm going on Howlett Hill Road, and I drove all the way up to Casson Road and then turned there, this would take me 6.5 miles. But no one would actually do that. You wouldn't. Love those announcements. You would instead take Corporal Welch Road. So what you would usually do is obviously take that shortcut rather than taking Casson, going all the way up to Casson Road. So instead of 6.5 miles, you would only have to go 5.9 miles. So it saves you that little trip of having to go over here. So a catalyst kind of does the same thing with activation energy. So if you look at a potential energy diagram, what a catalyst is going to do is it's not going to change where you start. It's just going to give you a little shortcut right about there, and it's not going to change where you end up either. And this doesn't matter if you have, an endo or exothermic reaction. It's always going to just shorten that energy hump. And I have some examples of some catalysts, but I want to go back and look at these graphs first. So this graph that we looked at here already, if we put a catalyst on here, it would do that. If we look at this graph now and see what changed, we're still starting at 40. We're still ending at 20. Our activated complex is now a little bit lower, okay? So this is going to now be less than 50. Our delta H does not change. Our net energy does not change when we add a catalyst. My reaction is still exothermic. Now my activation energy is lower. So this is now going to be less than 10, which essentially makes it easier for this reaction to happen. If we look at another reaction right here, if we look at the reaction as written, our reactants are 5, our products are 3. We have to get up to an activated complex of 6. Our delta H is going to be 3 minus 5, or negative 2. This is also an exothermic reaction. If we look at our activation energy, it's going to be 1. If we wanted to lop the top of this guy off with a catalyst, the only things that are going to change on here are going to be the potential energy of my activated complex is going to be lowered, and the activation energy is going to be lowered. Everything else on this is going to be the same. So you can carry over every single value, 5, 3, negative 2, and it's still exothermic. So to give you a couple quick examples of some ways that catalysis happens, you have a catalytic converter in your car. And this basically helps combustion happen in a way that prevents certain environmental toxins from getting out into the air as easily. So you have actually precious metals that are involved in doing this that are able to they're porous and they're able to kind of grab onto some of the exhaust gases and prevent them from going into the atmosphere. And this has a nice honeycomb shape that you can see here that really gives you a lot of surface area to help the reactions happen, so that instead of these gases going out into the atmosphere, they're able to be stuck in your car and react to make other things. You guys might have learned about lock and key enzymes. Enzymes actually hold on to molecules and help either break them apart or hold them together so that they're able to react. And this is another catalyst site diagram where you see you have the surface area right around here that kind of holds on to molecules and helps them react with one another. So very often it just kind of helps basically hold things in place so that you get the types of collisions that you need. So this is a platinum catalyst functioning to basically break that double bond in that ethene molecule and allow you to make it a saturated hydrocarbon by holding it onto this reaction surface. One thing that's talked about a lot is the idea of hydrogen fuel cells. Hydrogen fuel cells, unfortunately, do require for this amazing reaction to happen a very expensive platinum catalyst, but with that, you're actually able to take hydrogen gas, combust it with oxygen, and you give off H2O, which would be nice to be able to drive around with a car just simply giving off H2O.